Hello everyone, my name is Calderon, and today we'll be talking about the bomb calorimeter. The polar oxygen bomb calorimeter is used to measure the amount of heat that's released from the combustion of solid or a liquid sample in the oxygen bomb. This oxygen bomb is standard, so it is in widespread use today. The presentation outline will go through objectives first, summary of the apparatus, the thermodynamic relation, the outline of the procedure, and also discussion. The objectives are to become familiar with the physical principles, procedures, and analysis techniques associated with the oxygen bomb calorimeter, as well determine the thermal capacitance of the calorimeter and determine the gross heat of combustion of the samples provided. Quick summary, so the calorimeter is designed to measure the heat that's released from the combustion of the solid or liquid sample in the oxygen bomb. In other words, it makes it possible to measure changes of the internal energy of a system due to a reaction. In this diagram here, it's a brief diagram. So we have the insulating container. We also have the surrounding water with the stirrer to provide a uniform water temperature. As well, we have the oxygen provided to purge out any air, and as well with the reactants in the sample cup. This is a quick schematic of what we will be working with. One thing to note is the surrounding water, the oxygen, the stir motor, and the ignition wires. This is a detail of the bomb. I'd say something that's very important is the ignition wires, as well as the two electrodes. So the thermodynamic relation, the first law of thermodynamics for a system provides for us Q is equal to mCV delta T. Q is the heat of combustion, and mCV is the mass times the specific heat, and delta T is the change in temperature. So what happens in this experiment? Upon ignition, heat is transferred from the internal bomb surface to the surrounding water environment by heat conduction. With the rising water temperature resulting from the combustion of the sample, it is possible to calculate the number of heat units transferred. The stirrer is used to maintain a uniform temperature throughout the surrounding water. No work crosses the system boundaries, and the system is assumed adiabatic. The temperature rises only a few degrees, so the system can be considered isothermal. The heat that's released during this reaction is called the heat of combustion. And the amount of heat corresponding to a unit mass of the fuel is called the heating value. So pretty much the sample will be loaded into a reaction chamber that's completely isolated. And as well, it is purged with oxygen to remove any of the air particles inside. Then it will be submerged in water with an insulated container. Once the sample is ignited, a thermocouple will measure the change in water temp. So this is a quick discussion. We want to estimate the thermal capacitance of the system. Our system includes 2 kilograms of water and 3 kilograms of stainless steel. On the slide, we have some equations that we'll be using. The first equation is mass times specific heat of the solid or liquid sample. That will give you the thermal capacitance. So we had to do it separately for one for water and one for stainless steel. For water, we got 2 kilograms times 484 joules per kilogram times Kelvin is equal to 8,368 joules per Kelvin. And for stainless steel, we got the thermal capacitance to be 1,380 joules per kilogram. The total system thermal capacitance is equal to 9,754. We then use that value to solve for the delta T, which is the known value for benzoic acid, 26.38 kilojoules per gram. And then we divide that out by the sum of our total system thermal capacitance, and we get an estimate of 2.7 Kelvin. So why do this experiment? So calorimeters they provide an engineered simple means of measuring the heating value of fuels. So in our example, we'll be doing one version of where we know the heating value and a second version where we don't know the heating value of the fuel that we are using. So what's the heating value that we encounter every day? First one is motor gasoline. That one has a high heating value of roughly 20,000 and a lower heating value of roughly 18,000 BTUs per pound mass. The difference between the higher heating value and the lower heating value of the fuel, it's depending on the case in which the water is in the combustion products is either liquid. If it's liquid, it'd be higher heating value. If it's gaseous, it would be the lower heating value. So this may be written as the high heating value minus the lower heating value is equal to mass times the latent heat of vaporization, which is HFG. Our predicted results, we are expecting a dramatic rise in temperature after we ignite the charge. then slowly return back to equilibrium. Sources of error would include human error or instrumentation error. Some quick safety tips: always wear your safety glasses, of course. Appropriate attire, jeans, closed-toed shoes. If unsure about the procedure, read over the manual and as well as your TA. After the experiment, returning equipment back to original condition. Like I said, if you're unsure about the procedure, go back and reread the manual or ask the TA. We are dealing with a bunch of dangerous equipment. These are my references: the textbook, lab manual, and some quick online sources. Any questions?